Hello everyone, my name is Sunil, and as a part of this some series of lectures that we are doing almost every week, we are learning EVPN and trying to scratch the surface of EVPN and what are those nitty-gritty details and some history and the big why behind EVPN. This is our third session in this series, and in this, before I start this third session, first of all, my apologies for the delay in posting this third session. Ideally, the plan is to post one video per week, but this got delayed, and there were two reasons behind it. One was that my plan initially to cover in this third session was different route types, basically, that we have in EVPN. And maybe then if the time permits we would have gone into one or two route types in a bit more detail. While I was preparing the content for that, I met one colleague in office, and he asked some fundamental questions based on the videos that I recorded earlier, the first and second. Is and then the first one in that was that why in the first place we have so many route types in EVPN. Like if you recall from the second session, if you haven't watched us, by the way, I highly encourage you to watch those two sessions. And in the second session, we towards the end, I had shown you that there are 5 routes, and that almost everybody knows that in EVPN there are 5 different route types, and if we add multicast, you add 6, 7, and 8 as well. So why in the first place we have so much of route types in EVPN? That was his first question. And the second was that he was asking, like, Sunil, you have covered in the first session that data centers have moved towards EVPN, service providers have moved towards EVPN, and now campus networks are also moving towards EVPN. But what was the big driver behind that? Why EVPN got so popular that now industry is looking at it as a unified solution? So these are the queries that I will be covering as a part of this session. And second reason for the delay is nothing but just some technical reasons that took some time for me to figure out that. So we'll not talk much about those things, but you got it right. One what we will be talking is why there are so many route types and why in the first place EVPN got so popular in the data center, in the SPs, what has exactly happened. And sometimes the response to these questions are in the past. So that is what we will do in this video, that we will dig the history and find out those key reasons behind big why EVPN came into picture in the first place in the industry. And then if you're planning to stay till the end of this video, you will also come to know that why there are so many route types. I will not cover those route types in this video because I'm expecting that the content that I have planned for you guys today is will make this video a bit longer. So including those will make it even longer. So I have parked that for the coming week. So and if you see that this video is a bit longer, I can put those timestamps for the agenda wise, so you can watch as per your convenience in those particular sections as well. So with that, one final note before we start is that even though I have made every effort to make this video suitable for beginners, I assume very basic networking knowledge while talking about the concepts in this video, but I feel that even the experienced user will also find it useful. So if you are someone who is there for quite some time into this industry, working or want to work or learn EVPN, you may watch this at 1.5 or 2x speed and slow here and there wherever you feel that the information is somewhat valuable for you. So with that, let's just get into our agenda. So we will be looking at first the network virtualization journey, why we are talking about virtualization, and here I will talk about that big why behind EVPN. So in this, we will not be talking about EVPN apart from the definition, but we will take a step back and cover this network virtualization. And while talking about this, we will also talk about our second topic, which is scratching the surface of VXLan. And then we will connect these two dots, that why for the VXLan EVPN came into picture. I will give you a different perspective today than what I had given in the second video. The second video was how it was decoupling that learning of the MAC address versus distributing it. But in this, we will look at some more aspect of that. And I will hope you will find it useful. And then we will end our discussion with building blocks of EVPN. What are those basic building blocks? And this part is mainly for the beginners. So if you are experienced, you can even, as I was saying, watch it at a higher speed to save your time, or you can maybe skip it if you see that there is not much new to learn for you in this. So with that, let's just start with what exactly the network virtualization is. So here, before we get into any sort of virtualization, right, the first thing that comes whenever we talk about virtualization is the server virtualization. And this is the definition I took from Wikipedia, where server virtualization is the process of dividing a physical server into multiple unique and isolated virtual servers, and they do that by some software applications. So you say you have this big server, to divide it into multiple servers virtually. So basically one application is installed here, one application is installed here, one application is installed here. That way, basically you get the optimal resource utilization. There are high chances that when we deploy only one application on a server, we may not be able to utilize it till its full capacity. So that's where optimization of these resources, saving as well. Like now, if I virtualize, I don't need to buy that many physical boxes. That had given tremendous advantages to the customer, and that was the reason that virtualization got very popular. It had seen exponential growth, that even virtualization as well started from servers, quickly penetrated onto the storage side, and then people started talking about network virtualization as well very soon. How can we virtualize the network and take advantage? So the virtualization concepts or the thought process behind bringing the virtualization to the networking was same. Basically, when a resource gets virtualized, it can be shared by multiple users. So here, if we just go with the definition of virtualization, the network virtualization is carving up a physical network into many virtual networks. Just think about it, that you have this physical network, and in this physical network you build so many of such tunnels that you can dedicate one tunnel for one customer. So that way you are utilizing or the network, or you are optimizing the utilization basically of the network. So now in this network virtualization, what exactly is the role of EVPN? So EVPN, what it do is, like, it's actually a technology. And again, I'm just covering the definition here. We will go back to our concept slides after this. So EVPN is, let's say you have your layer 2 network here, you have your layer 2 network here, and in between you have your WAN, let's say, or some sort of L3 network. So with the help of this technology, you can connect these two as if they are directly connected. That is your EVPN is. And you basically construct this L2 network over this underlay of layer 3 network. But what are these virtual networks? Before we get into this EVPN, this whole series is dedicated to EVPN. We will be talking about EVPN in the upcoming decks. But here, let's take a step back and study different types of network, right? Types of virtual network. What I mean by type of virtual networks, you talk to any network engineers, when even a beginner level person, they will be able to explain you the concepts of VLAN, VRF, right, L3 VPN. All these were sort of uh, virtualization, where the network was virtualized and utilized in an efficient way, be it to limit the broadcast time, or be it isolating or segmenting different layer 3 network, if we talk about VLAN or VRF. So I'm pretty sure you know this. If not, there are so many videos that talk about these basic concepts. My point of this slide is not this. Let me show you something else here. That you have this, let's say, series of switches. I'm taking some 4 switches here, SW1, 2, 3, and 4. And if I want to carry or configure something in terms of VLAN, what I will do is I will configure that VLAN. Let's say it is VLAN 10 here. Then I will configure that here as well. We'll configure that here as well. And then here as well, to have that end-to-end communication. Same way, if I want to configure layer 3 VPN, if I want to configure another VLAN, I need to follow the same step. So this is for layer 2. Now let's come to layer 3. Let's say same set. This time these are routers. So R1, R2, R3, and R4. And I'm configuring a layer 3 network which should be isolated, right? The requirement here is that network, whatever I'm configuring, should be isolated. So I will configure a VRF here. Let's say VRF red, right? Let's say this is VRF light, and this is a enterprise network. So if I want to keep this isolation, I have to configure that VRF red here as well, and here as well. Okay? Same way, nothing different. Okay? Now let's come to another example where we want to segregate again layer 3 network only, but this time again same setup for routers. we are using something else. So I'm configuring VRF red here, but here this is L3 VPN. This way I need to configure VRF red here, and I can have a communication between node 1 and node 4. This is how your L3 VPN works. This is how your VRF light works. This is how your VLANs work, right? But what is the difference? The difference is that here you need to provision these VLANs or these VRFs at every node, even including the transit one. But in case of L3 VPN, you are provisioning the VRF or configuring the VRF only on the ingress and egress. The transit code, there can be hundreds of those in between. They don't care. They doesn't need to know this, right? So with this thought process, just wear your thinking hat for a minute and see here what I'm trying to say. Even VLAN is a type of network virtualization, right? I'm virtual LANs I'm basically creating. That's what VLAN stands for, right? VRF is your virtual routing and forwarding instance, right? We had seen two implementation. So with virtualization, one thing that you can do is that you carry that virtualization information in some form into the packet header itself, right? Here the .1q .1x header that will go out of this, right? Sorry, .1q, that will have this Ethernet tag with this VLAN in the packet itself, right? And I need to provision this on all the nodes. So this is called as inline virtual network. Same goes for VRF as well, VRF Lite, that I need to create it on each and every node. That's where it is called as inline virtual networks. But here, this way, I can create simply a tunnel. It's a type of overlay tunnel, right? Where these middle boxes doesn't even know what exactly is going on, what exactly is being forwarded from through them. So we are overlaying a tunnel, and that's where these are called as overlay networks. Right. So a virtual network which is implemented with certain protocols, and I'm not going into the details of what all protocols you use to implement L3 VPN. Just understand this point that if the transit nodes are unaware of what exactly is being carried, then you call that as virtual network overlay. And this is laid on top of your underlay network. I would let that sink in for a minute. Right? So you understand that the difference that I was trying to point out. Now let's just clear this ink and see what we have on the deck. So virtual network can be classified into, first is the way in which the ingress node decide how it will associate that, basically be it so like putting it into VLAN 10 or putting it into VRF red, that ingress node. So that stays the same for VLAN, VRF or L3 VPN, no difference. But the second one is whether the transit node are aware of that or not. That is the second classification. And believe me, many experienced network engineer doesn't understand these concepts, or at least they don't know. They simply say that you just overlay something on top. And then I ask like, okay, isn't it VLAN is a virtual network? So why we need another type of virtual networks when we can simply live with VLANs or VRF? But now with this, you see this problem, right? That one is taking the pain and creating it everywhere versus uh, just creating on the ingress and the egress, and transit nodes are not even aware what exactly is being taken uh, through them. I hope this is clear by now, but let's understand this with a type of some simulation as well. Let's say I have this C1 and C2, and in the same way as I was showing earlier, there is this R1, R2, and R3. Now a packet just start in this direction. It start from C1 and want to reach C2. So I'm without taking any IP addresses and all, I'm just taking C1 as a starting or a source, and then C2 is the destination. So R1 knows that okay, C1 it is learning that route from other end, so C2, right? But when the packet comes to R2, right, R2 have no clue about where this C2 is because we haven't configured it. So it will basically drop this packet. But if we provision a tunnel, let's say a tunnel from here to here, and I will put these packets into this tunnel, then R2 will not even see that there is a packet from CE1 to CE2, right? So let's just do that. So what I will do is, same way, the packet is going from CE1 to CE2. When it reaches on R1, what R1 will do is, R1 will basically put that into a tunnel, basically will wrap it around and put R1 as a source and R3 as a destination. Then R2 will understand that, okay, I know where R3 is because this will look at the top packet. R3 is, it will send the packet towards R3. R3 will see that, okay, I'm the destination of this packet. So let me just open it up. So once it open it up, it says, sees that inside packet, and this packet need to go to C2. C2. So what it will do is it will send it towards C2. So that is how your overlay network forwarding in highly simplified terms work. This is not a L3 VPN class. This is not a L2 VPN class. So we are not going like how R1 learns about C2, which is behind R3. So that can be parked for some other lectures, or it can be a different lecture altogether. But idea for today is, this is how these overlay tunnels are built, right? So this is just one customer. There can be another customer here, right? Let's say it is C3 and C4. So I will make one more tunnel for that, right? Same way, another customer, another tunnel, like that. And the good part is R2 doesn't even know whether he is carrying 10 customers or 100 customers. Believe me, this was one of the single point where L3 VPN got so popular that I haven't heard of any SPs so far who is not using layer 3 VPN, because the key reason is that it is very simple to deploy. If a new customer comes, you only need to configure them on the ingress and egress, or you don't need to do anything. But in this case, let's come back to our discussion of virtualization. Let's say if this customer is using 10.10.10.1, this customer is also using 10.10.10.1 here, 10.10.10.2 here as well, the same IP address. How R1 will know that this belongs to C4 or let's say tunnel 2 versus tunnel 1? What I'm trying to say is C3, C1, they are two completely different customers. They can use same IP addresses. How does EVPN, again, L3 VPN also faces the same issue, but since we are talking about EVPN, I'm just talking about that, how EVPN separate this out. Right. So before that, let's just understand this with the analogy that the network addresses, of course, it should be unique, right? It's like your postal address, right? If I talk about myself, let's say there is this address of 133 Heritage County. It is in Bangalore, and Bangalore is in Karnataka. So in Karnataka, there cannot be another Bangalore. There has to be only one Bangalore. In Bangalore, there has to be one society, which is Heritage County, and in that Heritage County, there has to be only one house number with this. So I have to make this unique so that if somebody is sending me some letters or something, that can be delivered to me. So in case of cities, states, countries, it's the government that is doing it, right? But does that mean that here what I'm saying is, the point that I'm making is this uniqueness that I'm talking, it should be in that particular country. Like for example, if I talk about India, there can be only one Karnataka, there can be only one Bangalore. But does that mean that there can be another Bangalore somewhere else? Why not? Right? End of the day, what we are talking is like these identities should be unique within that particular container, right? Within that customer environment, there should not be any conflict, but between customers, it can overlap, right? And to give you an example, like for example, there is a very famous city in India which is called Kochi, but Kochi also exists in Japan as well. There is a city called Patna in Bihar, but if you are a resident or if you have ever got to Scotland, there also there is a city name called Patna. Though it has its root in the colonial era of India, why there is another Patna in Scotland, but I'm not going there. And our famous capital, Delhi, which is in India, the heart of India, but there is a Delhi in USA as well. So the point here is that it should be unique within that container itself, right? So on the same line, if we come back to our discussion, the virtual networks, right? The MAC address needs to be unique only in that connected layer 2 network, or an IP address needs to be unique only within a layer 3 network, right? So how we are making sure that they are unique and how we deal with these overlapping IP addresses, right? You may have these questions. So part 2, I will cover that as part of that building blocks of EVPN. If you remember the agenda slide, I will cover it in the later part in the same video. So hold this thought, like how R1 is making sure that the prefixes that it gets are unique, right? We will cover this. But before the benefits of overlay, I had already told you, right? One is that the network overlay versus non-overlay, or you can call it as inline virtual network also, which are like your VLAN, VRF Lite, whereas overlay I had already told you this is L3 VPN, because the network core does not have to store forwarding tables for these virtual networks. And the second benefit is that it allows the rapid provisioning of virtual network. All I need to do is need to provision the network on the ingress speed, right, and egress speed. And I'm good to go, right? So that enables me to uh, provision these network at a much faster rate. So now coming back to these virtual networks, what exactly you are carrying on these virtual networks, right? We had seen that these virtual networks are provisioned in some form of tunnels. We are drawing those tunnels. So these tunnel headers, right? This is a tunnel which is built on top of a network, right? So that means that there should be some IP source address, IP destination address for that tunnel also, right? So these tunnels can carry either a layer 2 packet or it can carry a layer 3 packet, right? And same way their header can be constructed using L2 or L3. Let's look at some of the examples. Q in Q, Trill, Mac in Mac. These are all example of layer 2 tunneling, where you have a VLAN 10, Q in Q, you encapsulate that VLAN 10 into another VLAN and you carry that in the network. The network nodes will not see the inner tag. Same way Trill and Mac in Mac work. The example for layer 3 is your VXLan, GRE, or MPLS. Even MPLS is also some form of tunneling. But the point that I'm trying to make here, one more here, is if it is a layer 2 tunnel, it can only carry L2 payload. But if it is a layer 3 tunnel, it can carry L2 or L3 payload. Right? And there are like different tunnels that exist. You may ask me like why there are so many of these tunnels that exist. These are created for different use cases, like VXLan that we will look at this chapter, why VXLan was created. MPLS was created to solve some other forwarding related problems related to IP, right? And all of them use different semantics. For example, MPLS, right? It can be an MPLS value, that range in the header can be 2 raised to power 20. Right? So that way you can have somewhere around 1 million labels. But if you look at VXLan, it's a 24-bit field. That means you can have up to 16 millions of VNIs for VXLan. So all these were different range that were allocated, different number of bits were allocated for different encapsulations. But I have not seen any network which is using at least this many range of VXLANs. So we should be good with that. So before we move on to our next section where we understand VXLAN, actually let's look at some time understanding about the consequences of tunneling. Right. The first one is load balancing. I was talking to an engineering guy, and we were discussing about how a network load balance. Let's say there are two links between two routers. The packet comes. How does it send those packet here and here? So basically, the router look at the source address, destination address, and port number information to load balance the packets. But when these tunneling concepts started coming in, different type of tunnel, GRE, MPLS, and then IPsec, right? All these are what type of tunneling mechanism. You basically encapsulate that packet and put your source address as R1, destination address as R2, right? So the transit node in between, how they will take the call for load balancing. So this was the issue with tunneling. In fact, in MPLS, if you are somebody who is from service provider world, this was one of the key problem where labeled packets were not getting load balanced, and industry had came up with some sort of entropy label, some other mechanisms, provisioning multiple traffic engineering tunnels. And again, those who are experienced watching this will understand this part. Beginners, you just understand that if my source and destination packet is encapsulated, let's say this is for customer one, there can be another customer, right? But they will also get encapsulated like this only. So how the transit node will load balance when they will calculate the hash based on source and destination? For all the tunnels it is same, so it will not be load balanced. How VXLan solves this, we will see in subsequent lectures, because today I think there is a lot more that we have planned, but I will park this thought, will tell you how VXLan solves this in some of the upcoming lectures. Okay? So this was one issue. And then the other issue was about the server NIC. Now, what could be the issue with the server NIC? So, what happened with the virtualization as virtualization was evolving, right? There was this server NIC, and then you have this application hosted here. So, packet processing like TCP offload, checksum calculation for IP packet, right? And some other operations were offloaded to this NIC itself, the server NIC, so that these applications get the processed packet, and that way we can save the CPUs. But if the packet is encapsulated, let's say if we are using some sort of tunneling from server to server, right? The network is just IP forwarder here. Right? So in this case, what will happen? The NIC that the packet will hit is an encapsulated packet. And in fact, those of you who are tracking or know VXLAN from the start, VXLAN was actually designed to start from here itself and end at here. So VXLAN is also a sort of tunnel, and if the server is processing that encapsulated packet, TCP offload, checksum, all these it will calculate on the outer IP packet, and then it will give that to the application which has to process that decapsulate packet. So those offloading advantages that were there has been nullified with the tunneling mechanisms. Later on, there were some enhancements that suggested that even server NIC can look at these encapsulation, but that didn't fly well. So this point is actually a very important point in our discussion. Please remember this. I will touch base this point again in VXLan, and then we will see what are the problem that has given birth to EVPN. But for now, you understand this, that if we have tunnel end to end from server to server, we are losing the advantages of a NIC doing TCP offloading, calculating the checksum and all, because the packet is encapsulated. Hope that point is clear. Let's move on. The third one is quite evident, MPU, because if you are, let's get rid of this ink first. If you are someone who is doing this tunneling in the network, so I had shown you, right, that there are these packets, C packet 1, let's say C2, and then you add on top of this the encapsulation. If you remember the earlier animation, so basically you are adding more headers, more headers to the existing packet. That means your packet size will increase and you need a larger MPU. Normally with VXLan, we say that you should have an MPU of at least consider some 50 bytes of overhead over the MPU. But not going into the design and all, just understand as a consequences of tunneling, your packet size will increase. Right? So now, I hope you understood all these concepts that we have discussed so far with respect to network virtualization. What are those different type of virtualization, inline versus overlay, the advantages of overlay, and then I left some question open, like how you keep address unique versus this server NIC issue. I just left it open. So these points let's discuss in our upcoming section. If you want to take a pause, we are already like 43 minutes into this video. Go ahead and do that, and then maybe you can come back and go to the next section, which is understanding VXLan. So again, for VXLan, I'm going to talk about how does VXLan work, what VXLan is, because there are so many videos that already exist on internet. You may go ahead and watch those. What I will do is will just touch base on one unique thing, one point that is important about our discussion that we are doing in this video. So first thing, the definition of VXLan is that it is again a tunneling mechanism that mainly connect L2 over a IP network. So your IP network is layer 3, right? So that's how you connect your layer 2 network by using VXLan. But the thought that I wanted to touch is why we needed another type of encapsulation. There were already so many encapsulation. I had shown you a couple of them already. GRE was one of them, right? So why we need another encapsulation? An answer to this actually goes back into somewhere around 2009 to 2010. where VMware was riding the wave of virtualization, and AWS, Amazon with the AWS, was giving the offerings to its customer that they can move their workloads into the cloud. So what was happening is that VMware wanted to simulate or give its customer the freedom, or basically to provision something called as private cloud. That is private cloud. I'm sorry for this. So this private cloud, and for that they reached out to giants like Cisco, and wanted to brainstorm that how can they give this private cloud services to their customer. And their key requirements was that there could be these layer 2 payloads distributed anywhere, and they just want to connect these. How they want to connect it, VMware choice was to connect it over IP. So you have your IP network, and over that, doesn't matter where they want to place their L2 workload, it should communicate. So people understood at that time that okay, to connect this, there is some sort of tunneling is needed, and they considered multiple options. MPLS was one, GRE was one, but they were ruled out for one or other reason. For example, MPLS, it was mainly the service provider side of the stuff, and VMware primarily looking at the data center at that time. So MPLS was ruled out. GRE was also ruled out because it was some generic IP encapsulation, and the people at that time, they wanted to be very predictive, right, in terms of the load that this new encapsulation will carry. And another thought that they were thinking is that if we can have this tunnel, and again I'm going to the server side of the things, let's say this is the NIC. So if they can have this tunnel start right from this NIC itself and build over an IP network, so that way my network will be very simple, and I will have this tunnel initiated from here to here. So to carry something over IP, they came up with this new tunnel which is called VXLan, and I will show you VXLan header and everything in the next video. But for now, this is just the thought process behind VXLan. So initial proposal for this new tunneling was to create it from server to server, and that's where, if you remember the term called as SDN, software defined networking, this has its root here, where the vendors like VMware, what they thought is that when a user is creating, let's say, a new VM, that new VM will definitely need a network, so that new network, and what I mean by network is a new VXLAN tunnel can be created via that orchestrator itself, and once that VM is taken down, this tunnel can also be taken down. So this was actually one of the very initial thoughts behind the software defined networking. But this thought didn't fly well because the issues that I had explained you earlier, like the NIC server issues in our the previous step, where these TCP offloading, IP checksum calculations, there was so much of the stuff that over a period of time, the industry had offloaded to the NIC. And if we go with this approach, it was very difficult to manage that. So what they did is that they thought that let's not go with NIC to NIC, but at least we can go with this VXLan tunnel from network to network. So let's just clear this ink and see what we have on the slide. So as I was explaining, right, the VXLAN was designed to allow these compute nodes to be NVEs. What I mean by NVEs is network virtualization edge. Means that tunnel starts from the server itself, with network being a simple forwarder. And multiple companies like VMware, Merge Networks, they just went behind this idea, came up with this fascinating term, software defined networking. In fact, this NSX solution was all about that. And as I was saying, right, these were the network which was originally proposed as software defined network, but it didn't fly well because of the reasons that I explained related to those NIC offloading. So that's where the industry started looking at an alternative approach. And that alternative approach was to have something traditional to rely on. And that's where vendors like Juniper, Cisco, they came up with this BGP. That instead of having these tunnel from server to server, where the server administrator, when he's creating the server, is creating a net, can create a network as well. They thought that let's keep the network separate and have some sort of controller, less kind of architecture, and go with the BGP protocol itself to circulate the information. Now, what type of information that was being circulated? So, ideally, from the BGP or any control plane that the industry was looking at, there were only two key asks that they were looking at. One was that they needed some sort of mapping mechanism between the destination address and the correct egress NVE. What I mean by that, let's say you have this R1, R2, R3, and here behind R3 I have, let's say, MAC XX. So a packet comes from R1 with source as A.A and destination as X.X. So mechanism for the destination address. So this X.X to the correct egress. What is the egress in this case is R3. So if somehow this R1 can know or learn this, that X.X is behind R3, so what it will do is it will encapsulate this packet, put R1 as source and put R3 as destination. That is what your point number 1 means. That inner destination address mapping to the correct egress NVE, and again these are called as NVE in VXLAN term, network virtualization edge switches. Right. If you are from MPLS world, think of it as a P devices. And the second ask from the control plane was, let's get rid of this ink. Second ask was that let's say this R1 again I have R2, R3 and R4. Let's say there is a network for customer 1, CE1, who is, right, let's say there is a this cloud type infrastructure. So CE1, one customer, it has only its branches on R4. There is another customer, let's say A1, it has only its branches of connected to R1 and R2, right? So A1, A2 are only connected to R1 and R2. C1 and C2 are connected to R1 and R4. How does these NVEs can communicate this information? That R4 can communicate that, okay, look R1, even though you have customer A1, C1, and maybe some more, I am only interested in C2. Don't send me all other routes. Or if you are sending it, I will discard. On what basis it discard? Right. Otherwise, it will be a full mesh, right? Why should I take the route of A2 on R4 when I don't have that customer, right? I hope you got it, right? So this is our second question. Remember, there was first question around how we avoid these overlapping addresses, and the second question is how we make sure that R4 who is interested in the customers which are locally connected is able to convey this information to R1 that only send me those routes. So these are the two problems I think which are unanswered. I had already answered that server NIC issue. So now let's just look at these, and we will find the answer for these into the building blocks of eBGP EVPN. So this is our last block, and here we will also find out the answer for like why there are multiple route types that exist. Right. If you want to take a quick break, go ahead and take. We are already 1 hour into this session, but I promise there is some more that is left, and then we will wind up this lecture. Right. So I hope you are back or you want to move further. So let's just go ahead. So we had seen this, we have even discussed in our session 1 and session 2 as well, that BGP was decided as a control plane protocol for EVPN. And we had also seen that VXLan, though initially proposed from server to server, didn't fly well. So it was offloaded to the network side. And then in session 2, we had seen that VXLan initial mechanism of working flood and learn didn't work. So that's where they came up with the approach of BGP. But now in this part of the lecture, we will look at what are those building blocks for BGP. One is this peering model, and another one is how does the BGP exchange the routing information. So regarding this, we will discuss this in our upcoming lectures, where how you can connect your underlay, right, and how what protocols you can use here, and then how you use BGP in the overlay. So that discussion, already this video is long, so we can park that. But here what we will do is we will mainly focus on this second bullet, the design guidelines for peering model, what are the best options and all. I will cover later in this series. So we had seen this evolution of BGP, right? The BGP is the protocol which was designed to transport IPv4 information, but then slowly VPN v4 was added, VPN v6 was added, IPv6 was added, multicast was added, and all of these address families that I'm talking, like VPN v4, VPN v6, IPv6, MVPN, right? All these were address families in BGP. So the AFI, address family identifier, and subsequent address family identifier or indicator is configured in the BGP so that it can communicate to its peer what address it basically want to send. So this information is getting advertised into the BGP open message, and there it exchanges this AFI slash SAFI in terms of the capabilities. Now, if you are somebody who is a beginner, you haven't heard of concept of AFI or SAFI or whatever. One, this is not a class that talk about this, but to give you a high level idea that BGP from one end to other end transfer routing information. That routing information can be related to IPv4, it can be related to IPv6, right? But then the other side should understand that, okay, this is being sent for IPv6. Or there are other examples that I had covered here. So all these that BGP do, it do in terms of AFI and SFA, SAFI, sorry, that was a mouthful. So what I mean by AFI, let's take this example. For VPN v4, AFI can be your IP and SAFI can be unicast, right? Or for IPv6, AFI can be IPv6 and SAFI, subsequent address family indicator, can be unicast or it can be multicast, right? So you see these two level of segregation that BGP exchange when the session comes up, and BGP figure out that, okay, what the neighbor is able to support and what I am able to support and whatever is common. So these are capabilities, they get negotiated at the time when the BGP peering comes up. And we can look at maybe in some future BGP class, because this can be a whole topic altogether, but just understand, if I'm supporting IPv4 and IPv6, this side only support IPv4, then only IPv4 capability negotiation will work and IPv6 will not be negotiated, right? So then, so the BGP peer exchange this network information if both sides, this is important and that was the point I was emphasizing, both sides advertise an interest that, okay, I am also ready for both of these address families, right? So that's where the capabilities get negotiated. So we have talked about AFI for IP, SFI for IP, IPv6, right? For EVPN, AFI is L2 VPN and SAFI is EVPN. So that's how BGP advertise that, okay, it is interested in advertising L2 VPN and that too for EVPN to its peer. Right? And as a key takeaway from this slide, again, search on the internet. If you still didn't understood this, there is a lot more content exists on AFI versus SAFI. But the point that we should take to the next slide is this one, that AFI for L2 VPN, because we are studying EVPN here. AFI is L2 VPN, SAFI is EVPN. Right? So EVPN, as I was saying, maybe let me just clear this thing. EVPN is designed as a SAFI family for L2 VPN AFI. Right. Now let's talk about route distinguisher. To give you a very simple example of route distinguisher, let's say there are two Sunil in a class. You come into the class and you call Sunil. I will raise my hand, other person will raise his hand as well. But if you add this suffix, that Sunil Pareek, I will only raise my hand, right? So you are adding this additional information, this suffix, or it can be a prefix as well, something that make my name unique in that whole class. That is what your route distinguisher is. Route distinguisher is whenever you exchange VPN addresses, BGP prepend this 8 byte RD, and this RD and address make the address globally unique. Go back previously in this video where I was emphasizing this point, that how virtual network avoid these overlapping IP schema. So what they do is they get 10.10.10.1 from customer A1, they get 10.10.10.1 from customer A2, for customer B2, let's say, to keep them separate, A and B. BGP will append one RD to A1, another RD to A2 to keep them unique. This is how the addresses are kept as unique and the job of RD. Right, so this is just emphasize the point that I was saying. Virtual network allow the reuse of IP addresses, but if we append the RD, it makes them unique. Now remember, there was this second question that I was asking you guys. You have this R1 where you have multiple customers, and there is this guy R4 who is only interested in one customer, let's say A1, not this one. Let's say this is B1, right? So R1 only want route for A2. So this is the job of route target, where it allow the NVEs to convey the virtual network it is interested in. I will let that sink in for a minute. R1 will send the route for both BGP route, for A1 and for B1. But because we have route targets associated with this, R4 will only receive or only import routes for A2 only, and it will discard B1 to save some space. And why exactly need those B route? Because there is no customer there. That is the job of route targets, right? And in fact, let me tell you this with a very simple story. And how does actually BGP process a route? And what happens is, like, and I believe this fact that if you get a good teacher, understanding of the concept is very easy. He can make your life. No concept is difficult if the person in front of you is explaining it very well, right? So when I was in school, there was our this principal who have very unique way of teaching, and I had learned so much in my early life from him. So one day, what happened when we were in 10th grade, he called us and he told that there are certain gifts that he want uh, these to be distributed to the kids who are there in class 2, 3, and 4th grade, basically. And what happened was there was some event, all these children took part into that, they performed well, so he just wanted to reward them. So he said that, guys, he called me and one of my friend that you take these gift and distribute these to the children of these three classes. He thought, okay, this is a very simple job. He said that, okay, sir, we will do it. But then he was actually very generous. He said that, okay, there are like multiple of these gifts that I bought it from them because I was very happy by looking at their performance. So you take all of them and distribute three or more per child. Like, don't just restrict one gift per child because already there are more. So you give it to them. We were like, okay, we will give these gifts to them. And when we get into the class, we had given started giving the gifts. So me and my friend, we distributed them, and guess what? All of them were very happy. But then this happiness lasted only for few minutes. When they started opening the gift, they were a bit of upset. And why they were upset? Because and this is applicable to every kid. No matter how exciting gift you give them, but if you give them the same gift two times, they will be okay to receive it. They will be more happy if you give them multiple gifts, but of different type. Let's say one is a ball, another one can be some toy or some Barbie, depending on like the child. So, but the problem that we had, right, all these gifts were packed, and we didn't know that like what is inside these gifts. So we simply picked up the boxes, given multiple boxes. So here is, let's say, kid one who got three boxes, but all three boxes have the ball. There was another child, a girl child, she got three boxes. All three boxes were having some badminton rackets. So they were like asking what we will do with that. They started making some noise, and our principal also came in and he said that thank you to me and my colleague that you had completely screwed this up. So we realized our mistake. We didn't foresee that it is coming. So we apologized and we moved on. After a few days, he called us for the same task again. And he said that again, we need to distribute the gifts to the same group of childrens. And here are these gifts. Go ahead and distribute, Sunil. So this time we learned from our mistake that we did last time. And what we did is that I sat with my friend and said that, okay, all these gifts are packed. So let's just see and group the similar gift so that we give not give one child the same gift twice or thrice. So he agreed to this approach, and what we did is like we have written some numbers like, okay, one, let's say one, one, one. So whatever, wherever we have written one, it was having some sort of ball inside. Then there was, we have written 2, this, wherever we have written 2, that gift was having some other toy inside it. But then there was another problem as well in when we were previously distributing the gifts. What happened is that there is this grade 4 child who got a ball which was actually suitable for a kid of class 2. Now it was a ball, but it was for a smaller kid. So he didn't enjoy it much. And cherry on the cake was that he got multiple of such balls. So we wanted to avoid this second level of problem as well, that we knew that all these boxes which are numbered as 1 have balls, but some of these boxes have a bigger football and some of them have that smaller ball for a kid of grade 2. So then what we did is we wrote another number here. Let's, okay, this has, wherever the 4 is written, have a bigger ball. Wherever we are writing 2, that have a smaller ball. Let's say for a ball for a child of grade 2. Right? So that way we have, and then for the gift 2, which was having another toy. So this toy was suitable for kid of class 3, but this toy was suitable for a kid of class 2. So now you see that there are these 2 numbers. So when we got into the class, we simply told, and again I'm not writing the number on all this, it's just to explain you that we got into the class and we said that there is a 1 number written at the top, 1 number written at the bottom. So you should pick from the number that is written at top only 1 item from that. Let's say if you are seeing that there is number 1 written and you have already picked up 1 gift with number 1, you should not pick another gift with number 1. Okay, you go ahead and pick with number 2 written at the top. And then these ask sir, they used to call us sir, sir, there is a number written at the down also. So that we said that that is actually your grade. So if a number 2 is written, so only class 2 boy is supposed to pick that. So that way a kid from class 2 came, he first looked at 1, so okay, this is a gift, and then he looked at this number and he picked up this, and then he picked up this. So he got 2 gifts, and when he opened, one was a smaller ball, another one was a smaller some toy. He was very happy, and our approach worked, right? So, but why I told you this story, why or what it has to do with the title of this. So first thing is that we need to make these gifts unique. Right, there were some boxes which were having identical items, so we needed some way to make it unique so that we don't mix up and end up giving the same to multiple or same child. So we make them unique by writing a number on that. So the box with number 1 have only balls, but now these balls, right, some of it have football that we need to give to the child in grade 4. Some of them have a smaller ball that we need to give it to the child in grade 2. Right. So now let's relate this story to the concept of RD and RT. So this basically value can be your RD, which was making unique out of all these 100 boxes. I can look at this RD and tell that, okay, these are the boxes where there is a ball. And then this, you can relate it with RT so that the children, when they come, a grade 2 child he want a ball, but he only want a ball that is suitable for grade 2 only. So he will only pick up that, right? Based on his interest, grade 2, I will pick that grade 2 only, right? So that's a story where I wanted to explain you this concept. Uh, it was a little complicated story, but it was actually happened with us, so I thought of covering it. But here, if you see R1, I have one customer A1 here. Let's say where I am just giving this route, and then there is this B2 customer, 10.10.1. I have R2, R3, right? Here I have B2 site, here I have A1 site, right? So first thing first, when R1 receive the route 10.10.10.1, 10.10.10.1, what it will do is, it will add 1 column 1 column n n n.1. So this value is RD. In this case, it will become 2 column 2 and column n dot n dot n dot 1. So R1 knows that 2 to 2 represent this, and that's how I'm making these route unique, even though they were same, and 1.1 belongs to B2. But and now both the route propagate via BGP. They propagate in this direction, but then I add another attribute here which says, let's say uh, B colon B. I'm just taking an hypothetical example. A colon A, and here I have configured VRF A. Here I have configured VRF B. So this guy will see that B is configured. While looking at this value, it will only import this route, and this route, it will get discarded. Same way, here I don't have any B, this is RT, so I will discard that route and I will only receive 2 colon 2 and 1 because I have associated RT, that is AA, with this. I hope by now you are clear. So RT is the peer, like in this case R3, what route it want to import. RD is just to make that route unique. Okay, now let's come to our discussion and what we have discussed right at the start of this video, like why there are so many route types that exist with EVPN. So first of all, with EVPN, we are advertising the MAC address as well, right? That is true. We are carrying that layer 2 information as well, so we are advertising that. But if you go back to the previous slide where I was talking about AFI slash SAFI, so AFI for EVPN was L2 VPN, SAFI was EVPN, so both the places are taken, right? Now, if I'm advertising a single MAC address or I'm advertising a complete virtual network, I have no place to fit in the existing BGP schema. To make you understand this, let's say I have this IPv4 address, right? If it is a unicast address, what I will do is I will say my AFI is let's say IPv4, SAFI is unicast. So that way BGP knows that it's a IPv4 unicast address. But here the AFI place was taken by L2 VPN itself. SAFI place was taken by EVPN itself. So I have no place left to define the route type. What exactly is the route type here? And that is the reason, my friends, in EVPN we introduced multiple route type separately. So that's where you see that there are these auto discovery route, MAC advertisement, IMR, IP prefix route, right? So this was the slide where we ended our lecture 2 as well, and this is the slide where we are ending our lecture 3 as well. Don't get confused if you don't understand these route type. The purpose for today's session was to explain what exactly these types are. So sorry. The purpose for today's session was to give you the background of network virtualization and then basic building block of VXLan and then cover some sort of BGP. And in this, actually, the minimum required route types are RT2, RT3, and RT4. So with that, actually, this lecture here come to an end of it. And this is close to 90 minutes now that we are into this session. I encourage you, you can watch it in parts or increase the speed and then watch. And I hope there was something that was useful for all of you, be it at beginner level, be it at experienced gentlemen. And I would like to say thanks a lot for viewing.